Hey there, and welcome. Today we're going to tell the story of a very special family of molecules, the alkenes. Now they might sound simple, but trust me, they have a secret that literally shapes the world we live in. So, to get us started, think about this for a second. What on earth do plastic bags, rubbing alcohol, and the antifreeze in your car have in common? I know, it sounds like a riddle, but the answer is hiding in the amazing chemistry of alkenes. So here's our game plan. We're going to follow the life of an alkene. First, we'll get its basic profile. Then we'll uncover the secret of its double bond, check out all the wild reactions it can do, and finally see how this one little molecule turns into stuff we use every single day.
All right, first up, let's properly meet the star of our show.
Okay, so what is an alkene? Well, at its core, it's a hydrocarbon. But the thing that makes it special, the feature that gives it its entire personality, is right there. A carbon-carbon double bond. And I'm not kidding, this isn't just some minor detail. It's the source of all its power. It's the key to everything.
So before we get to the cool chemical reactions, where do these things actually like? What are their basic stats? Let's take a look.
For starters, alkenes are generally non-polar. That just means they pretty much behave like oil. You know how oil and water don't mix? Same deal here. Alkenes are insoluble in water, they'll just float right on top. But they're perfectly happy dissolving in other non-polar stuff.
Now for alkenes, size is a huge deal. The really tiny ones with just a few carbons are actually gases. As you make the chain longer, they become liquids, and if you make them really long, they turn into waxy solids. And the reason is pretty simple. The bigger the molecule, the stronger the sticky forces are between them.
But it's not just about size. Shape is just as important. Think about it like this. Imagine trying to stack a bunch of logs versus trying to stack a pile of baseballs. The logs, those are our straight-chain alkenes. They line up nicely, lots of surface area touching, which means they stick together better. That gives them a higher boiling point. But the baseballs, our branched alkenes, are all lumpy and compact. They don't have much surface contact, so their attraction is weaker and their boiling point is lower. Simple, right?
Okay, now we get to the really exciting part. The secret behind that double bond and why it's so incredibly reactive.
And here is the absolute key difference. Alkenes are way more reactive than their single-bonded cousins, the alkanes. An alkane's single bond is super strong, stable, it's content. An alkene's double bond? Oh, it's looking for action. Which, of course, leads us to the big question, why? What is it about having two bonds between carbon atoms that makes a molecule so ready to jump into a chemical reaction? The secret has a name. It's called a pi bond. See, a double bond isn't just two of the same link. You've got one super strong sigma bond that forms the main connection, and then you have this second, weaker pi bond. The electrons in that pi bond are just kind of hovering above and below the molecule, like this vulnerable, exposed cloud. And that cloud is basically an open invitation for other molecules to come and react.
So with this super reactive pi bond just sitting there, it's time to see our alkene in action. Let's dive into the world of transformations this thing makes possible.
The alkene's signature move is called electrophilic addition. Now that sounds fancy, but all it really means is that other molecules that are looking for electrons are drawn right to that exposed pi bond. And the alkene makes a fantastic trade. It happily gives up its one weak pi bond in exchange for two brand new, much stronger single bonds. It's a total chemical win-win. And you can actually see this incredible reactivity happen right before your eyes. If you take a solution of bromine, which has this really distinct red-brown color, and you add it to an alkene, that color just vanishes instantly. The bromine just dives right in and adds across the double bond. This color change is so reliable, it's a classic lab test to prove that a double bond is there. But these reactions don't just happen randomly. They follow a pretty predictable pattern, and it's governed by something called Markovnikov's rule. Think of it as a law of nature for these reactions, telling us exactly where all the new pieces are gonna attach. So how does it work? Well, just remember this little phrase, the rich get richer. When you're adding something like HBr, you look at the two carbons in the double bond. The hydrogen atom, our rich part, is gonna go to the carbon that already has more hydrogens. And the other part, the bromine, goes to the carbon with fewer hydrogens. It's a simple rule, but it predicts the outcome almost perfectly every time. But chemistry loves a good plot twist. And while Markovnikov's rule is the default, chemists figured out how to flip the outcome completely on its head. If you add hydrogen bromide, but this time in the presence of peroxide, the reaction goes the exact opposite way. We call it anti-Markovnikov addition. It just goes to show how a tiny change in conditions can give chemists total control over what they're making.
Okay, we've been deep in the theory, but now for the payoff. How does all this reactivity actually translate into the stuff that builds our modern world? The ultimate transformation for an alkene is something called polymerization. This is where that reactive double bond breaks open and links to another alkene, which then breaks open and links to another and another and another and another, thousands and thousands of times. These small individual units, the monomers, all join together to form one single gigantic chain molecule called a polymer. And this brings us right back to that question from the beginning. That plastic bag, that's polyethylene, made from polymerizing the simplest alkene, ethene. Rubbing alcohol, that's propan-2-ol, made by adding water across the double bond of propene. And antifreeze, well, that's ethene-1,2-diol, created by reacting ethene. 3 totally different things, all born from the simple reactive power of an alkene's double bond. When you really think about it, an alkene's double bond isn't a weakness at all. It's a gateway. It's a starting point for building bigger, more complex, and more useful molecules. It's the foundation for so much of what we rely on, which kind of leaves you with one final thought. What are we going to build with it next?